Alright, welcome to another video. This is a video where we're going to go over a chemistry first year in college exam paper. This is chemistry 2010-2024. So this is having sections A, B, and C. A good start for somebody who wants to review several topics at a go. And of course, the questions, the way I'm going to answer them will be sufficient to help you understand a certain section. But where necessary, I'll actually recommend certain videos that I've worked on to go deep under each topic. Starting with question 1, the correct oxidation number of iodine in iodide oxide is what? Okay, so when it comes to determining the oxidation numbers, there's some standards that we actually follow. So when you look at oxygen, for example, and hydrogen actually has got a valence, we use positive one, and then for oxygen we use -2 for the oxidation number. Okay, and other things that we actually tend to note is these transition elements are the ones that have got a tendency of varying the oxidation numbers. Okay, so we actually pay attention to, if you look at group 1 and group 2, these are metals. Okay, so group 1 and group 2, we're actually going to use their valence electrons, the number of electrons in their outermost shell, which are 1 and 2 respectively, matching to the group numbers. And then when you go to the other part of the periodic table, group 8 of course is already stable because they've got 8 electrons in the outermost shell. These are noble gases. For group 7, they've got 7 valence electrons. They need a single electron for them to gain stability. So in terms of oxidation number, it's -1. For group 6, -2. For group 5, they need 3, so -3. Carbon and group 4, this can also vary, but we'll actually have to calculate for this as well in most of the cases. Okay, so now let's actually see how we can apply whatever I've given you to answer the previous question. This is very direct. So when you look at a compound, the overall charge of a compound is given by the charge. If there is no charge, it's 0. In this case, we've got a negative, implying that the overall is -1. Okay, now how many iodines do we have in this compound? There's just one. So say iodine. You can use any letter of your choice. I'll use iodine I itself. And then we've got 3 oxygen atoms. Now the oxidation numbers of these should be able to be equal to the overall, which is -1 for the compound. Now iodine is what we're trying to calculate, and then oxygen, I said the standard is -2. It's in group 6. So then we can try to find for the iodine, which is unknown. So 3 times -2, that gives us a -6 equal to -1, and then our iodide becomes equivalent to -1 plus 6, which gives us a +5. Okay, so that's our answer for question 1. Okay, I hope that has given you an idea on how you can actually get to calculate the oxidation number of an element in a compound. Now moving on to B, or actually 2, the correct formula for cobalt 2 nitride. So this is where I say the transition elements, these actually have got varying oxidation numbers and usually given explicitly in the question. So when you say cobalt 2, you're specifying that the cobalt you're dealing with has got an oxidation number of a 2. So cobalt has got an oxidation number of a 2 in this case. And then nitride, that's nitrogen. Nitrogen comes from group 5. If you check your periodic table, nitrogen is in group 5. So group 5 elements have got a valency or an oxidation number. Let's say oxidation number is 3 minus, because it needs 3 electrons for it to gain stability. So we'll use these for our calculations. So to come up with a formula, the simplest way to come up with a formula is just to swap. That becomes the subscript of the other and vice versa. Okay, the same applies to the other side. So cobalt nitride, so we'll actually swap. So the cobalt, which was having the 2 plus as the charge, was going to go on the nitrogen, and then the 3 will go on the other part. So no signs when it comes to subscripts. So what answer is that? So that's B actually. Simple and straightforward, right? Now when you look at the next 2 questions, these are coming from electron configurations. This is actually, I've got a very good video. If you go to our site, if you're registered on our site, of course the link is in the description below, you'll find that we've got topics arranged, we've got videos arranged according to topics. And so when you go under chemical bonding, you find a section for the electron configuration. Okay, if not if not under atomic structure, it should be atomic structure chemical bonding. I'm now getting mistaken. So you find a section where I've talked about the electron configuration in very detail, but I'll still explain to help you understand. So the best way, or the easiest way to actually determine the electron configuration from the periodic table is we go by the shorthand notation, where you use the group 8 elements, okay, the noble gases. So it's called the shorthand. It's also called the noble gas electron configuration. So when you look at copper is in period, so period 1, period 2, period 3, period 4. So it's in period 4. Okay, so check the previous period, which is period 3. The last noble gas here is argon. Okay, so after argon, what comes next? So this periodic table can be divided into sections. So there's the S block for group 1 and group 2. There's what we call the D block, that is beginning from here and going down. Okay, and then this other section is the P, and then the bottom part is the F, which we don't usually use. So focus on the S, D, and P. Now for the case of our copper, we're already done with period 3 because we've already gotten the argon. So we'll straight proceed to period 4, okay, where we first of all meet the S block again. So the electron configuration will become, since I'm in the S block in period 4, so I'm going to write 4s now. So I need to move 2 electrons, so I'll put 2 for group 1 and group 2 in the S block, so fully filled up. Now this is where it's a bit tricky, actually interesting, in that the D block only exists beginning from period 4, but then when it comes to counting for the D block, we start with 3. So this is 3, this is 4, this is 5. So if you're in period 4, for the D you're going to use 3 instead of 4 for the period. So it lags by a 1. So, and how many electrons do we need to count for us to get to copper? So D block is starting immediately after group 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have a 9 there. This is where people get it wrong. So we've got 2 exceptions when it comes to electron configurations. If it was just another element, that would be fine. But for copper and chromium, there are some exceptions, in that they have got more stable structures with half filled or fully filled. They are more stable when they're either half or fully filled, the D block or the D orbital. So the D orbital actually occupies a maximum of 10 electrons. So for it to be stable, for chromium and copper, it has to have 5 or 10. Now in this case, if we check the D block, it's having 9. So we have to now excite 1 electron in the S to the D. So that will become 1, that will become 10. So that will be 1 and 10. Okay, this is where the exception comes in. So when you go to our answer, 4s, so you've seen that we ended up with 4s1 and then 3d10 and then started with argon. So in this case, the beauty is you notice that actually the section representing up to argon is basically one and the same, right? All the way up to 3s2, it's actually the same. Now the issue is on the S, the 4s and the 3d. It doesn't matter what you start with. So let's arrange it in the order in this question as put it. So some sections are starting with 3 and whatnot. D, the other one starting with the S. So let's compare. If you look at the first one, I can't see 4s anywhere, so that disqualifies. Equally disqualified. Equally disqualified. And electrical discomfort. Now this is where it becomes tricky again. I hope your eyes were more open than mine, because this is a copper 2 plus ion, so implying that it's actually gained. No, actually lost. When it's said positive, it implies it has lost. So losing electrons. Okay. So losing two, what would that actually imply? So if we lose two electrons, they're going to come from the D block. So we're going to remain with argon, and then 4s1, 3d8. Okay. Now that becomes 8, and then the s block is having 1. Now, is that necessary for us to remain with 1? Since that is neither half filled. So this is now a case where it becomes tricky, right? So this actually in its standard form remains the answer, because this is the ground state without losing. So after losing from the D, it remains 8. Okay. So I just hope I've not confused you there. And just for the sake of clarity, for somebody who wants to understand how these came about, all the way up to 3p6, so you can actually also do it from here. So I want to come up with electron configuration of copper all the way there. So this is the S, this is the P, and this is the D. So period 1, 2, 3, and 4. So for the first one, we'll start with 1s. So the first period is easy to present because it only has 2 elements with maximum of 2 electrons. So that's for the S. And then for the second one now, 2s. So in the S block again we've got 2, so it will be 2. And then we'll shift, there's no D. We'll go to this part now, the P. So the P, that's in this second period. So P occupies a maximum of 6 electrons, and if you count them, there are 6. 1, 2, 3, 4, 5, and 6. So 6. And then we go to the third, sodium and magnesium, which are 2. And then again the P, again 6 of them. That's how that comes about. And then you move to the next one, which is now the 4s, and then the 3d. Okay, so 3d, that would be 9. That's the ground state. And then after it loses it to, it actually becomes 10 there. And then after it loses, it becomes 8. So that's for the third question. Now moving on to the fourth question. Which element forms the 3 ions to attain the electron configuration? So 3s2 and then 3p6. So when you look at that, 3 negative, that implies we gained 3 electrons. So if you actually want to determine the actual element directly, you can actually just subtract, remove the 3. So it will become reduced to the 3 there. So 3s2, 3p3. So let's go to neon. Don't forget the electron configuration. It's neon, 3s2, 3p6. That was before removing the 3. So now we are saying this had gained 3 electrons. So if you remove the 3, or let's actually try to identify this one before we actually remove the gained electrons. So neon is there. Now we are moving to the third period. So the 2 electrons are there for the S block, 3s2, and then the 3p6 is going all the way up to argon, because there are 6, 1, 2, 3, 4, 5, 6. Now removing the 3 that were gained, that identifies phosphorus to be the one that is supposed to gain 3 electrons for it to gain this electron configuration. Is it there? Yeah, so the answer is D. Now if we go to 5, this is coming from chemical bonding. This is dealing with the electron geometry and the molecular geometry. So electron geometry is one that includes a set of lone pair electrons, and then the bent or the molecule doesn't include the electrons when it comes to giving the name of a shape. So let's look at that. Now, which one is going to give us a trigonoplanar and which one is going to give us a bent? So if we start with the first one, I'll show you the quickest way of answering this question. So if you look at phosphorus, phosphorus is in group what? Phosphorus is in group 5. So it was got 5 valence electrons. So 5 valence electrons, now it's connected to 3 chlorine atoms, meaning that it's remaining with a lone pair of how many? 5 minus the 3 that it's sharing with the chlorine atoms. So it's remaining with 2 electrons. So it will be something like P and then 2 electrons connected to 3 chlorine atoms. So something like this. Okay. For water, we know the shape of water. Oxygen, the central atom with 2 sets of 2 electrons of lone pairs, and then hydrogen. So oxygen is in group 6, so that counts for the 4 lone pair electrons with 1 electron taking part in the bond formation of hydrogen. Okay. And then sulfur dioxide. Sulfur dioxide is, where is sulfur? Sulfur is in group 6 just like oxygen. Now forming this is forming a structure. This is where it becomes tricky. So sulfur dioxide is actually a very unique structure. Yeah. So how do you draw it? Okay, so yeah, actually arguments. One is where you put the 2 double bonds like that with no lone pair electrons, or one where there's a double bond to one oxygen and then there's a set of lone pair electrons, which we're going to settle for in this case. So that's the best structure of sulfur dioxide. And for this one, that's carbon bonded to 3 electrons, 3 what? 3 carbons, 3 hydrogens actually. I don't know what's on my mind. And then on top here we've got a chlorine atom. Okay. So now let's try to identify the names. So identifying these with the electrons present like that, these ones are called the electron geometry. Okay. Now if you start with the first one, which is having 4 connections, what do you think is the electron geometry for such a structure with 4 connections in total? Okay. So these are the ones that we call the tetrahedral. Okay. So tetra from the word 4. So tetrahedral is this electron geometry for the first one. So already it's disqualified. Okay. Now the tetrahedral structure, if you remove the lone pair electrons, it becomes a trigonoplanar. This is a trigonoplanar with 3 that are bent. Okay, this is trigonoplanar. With the presence of the electrons on top, it was called tetrahedral, so which is not the required. So if you want to go details in trying to find out more about these names, you can just go to chemical bonding on our site. You'll find a video about the electron and the molecular geometry. And then of course for water, yeah, so when you look at this now, look at this, yeah, water. So what do you think is the structure of water with 4 bonds as well? Okay, so we can call it tetrahedral as well for the electron geometry. And then of course if we remove the 2 lone pairs, it becomes a bent shape. So it was tetrahedral, now bent. Now for sulfur dioxide, and so just a correction on this structure. This is supposed to be a double bond for a better structure, or the most desirable Lewis structure. Yeah? So this is the most desirable, unlike what I said previously. Yeah, so because this one's got like valences, zeros for each one of them. The former charges are zero for three of them. Yeah. So without the electrons, or with the lone pair electrons, the electron geometry, since we've got three parts, this is trigonal planar. Okay, and then if you remove the electrons, you can clearly see that it actually becomes a bent shape. Okay, so this is actually the answer. Then if you go to the other one, that one has got no lone pair electrons, so there is no difference between the electron geometry and the molecular geometry. We just have the molecular geometry, which of course is tetrahedral because there are four connections to the central atom. And that's the end for this section of the answers. Okay, so if you want to access the full video, the full solutions to the chemistry paper, kindly register using the link in the description below. Okay, you'll be able to access the full paper and a link to all the other topics in chemistry on our site.